This is just a short video about transresistance. Now, this took me a bit to figure out exactly what it was and how to find it. And through looking at various different texts and some of the Tektronix Concept Series videos that Vintage Tech has posted, and I will link their channel in the more info section of this video, I managed to accumulate a very simple, basic understanding of what transresistance is, how to find it, why it's important, and how this helps you find the H parameter HIE. So, a transistor looks pretty harmless, but it's not. Transistors have all kinds of stuff inside them. There is collector capacitance and base to emitter junction with the little resistor in it, and it's the small signal version for high frequency looks kind of scary. So we're not going to talk about that today. We're going to talk about the very basic mid-band version of the small signal symbol, which is this here. You're probably familiar with that if you study transistors. But what I want to focus on first is this little guy. In the emitter, there's almost like a resistor. It's a dynamic resistance. It changes with the collector current of the transistor. It's not fixed, unlike a normal resistor. So it's not really a resistor, but it is measured in ohms. I like to think about it as a variable resistor that changes with the collector current because that makes it really simple to think about and you don't have to worry about trying to wrap your head around it. This is called little r, little e. Now, if you've studied transistor circuits, common emitter amplifiers, the emitter degeneration resistor that you put to limit the gain and add stability to the amplifier is usually called RE. And it's usually a big R and a big E. To show the difference between this and the degeneration resistors that you commonly see, I call it little r, little e. And this is equal to 25 millivolts, which is the thermal voltage of silicon, by the collector current. Now, that is the constant. When that changes, the answer changes completely. So you have to know what the collector current is roughly to guesstimate what your little RE is. And then you can use that in your gain calculation, where usually it's your load resistor divided by your emitter resistor. But if you don't have an emitter resistor, or you have a bypass capacitor to ground, so if you have a resistor to ground, usually you don't count this guy because this one's usually big enough to not really worry about this one in your gain calculations. But if you have a capacitor bypassing it, that's a short at AC. Well, depending on how big the capacitor, but let's say it's big enough to be a short at AC down to even 10 hertz or something. Especially common in audio amplifiers. You don't divide, you don't get an infinite gain just because you've bypassed that, because there's still that little guy there, and that's when it matters the most. So now it's your load resistor divided by little RE will give you your gain. Usually that's in the order of 300-400, so definitely not infinity. So that's very handy for that. The other thing being able to find the transresistance helps you with is in your BJT model here for your common emitter amplifier. And you see here we have the very simplified version of it, where you have HIE, you've got your base terminal here, and you got your base current coming down here, and you have your collector terminal here, and you have your collector current here, and there's the current source that shows that the collector is current source coming down, and all of that exits through the emitter. HIE is the transistor's impedance. It's an AC characteristic that you find when you're doing your AC analysis, your small signal analysis. And it's basically, if the circuit in front of it was looking at the transistor, it would see HIE. Now, this is important because when you're trying to find the input impedance of a transistor amplifier, you want to consider this value because it could be all over the place. Depends on what your collector current is. It varies quite greatly with collector current. Now, why does it vary greatly with collector current? Because it's based on little re here, the transresistance. The HIE is the AC gain plus 1 multiplied by the transresistance, little re down here, or 25 millivolts over the collector current. So you can find what the circuit in front of it will be looking at by doing that. Now, if you have this resistor here, and let's say this capacitor doesn't exist, now you have to change this a little bit, and it becomes HFE plus 1 multiplied by the little re plus the, we'll call this the big Re, because now you have a resistor in series with it, and you multiply this plus this times the gain plus 1, and that gives you your input impedance of the circuit itself. Now, this is just talking about the transistor by itself. You grounded the emitter or bypassed the emitter with the emitter resistor with a capacitor. It's not called HIE when you add in big RE. This is just for the small signal analysis of that. Now, if you were to add big RE to the small signal model, you would see it like this, because the collector and the base both feed through the emitter through big RE. Now, so as far as I'm going to go with this, I just wanted to make a video about finding the transresistance. I always was confused by it until recently, where I discovered it's not that hard. It's very straightforward. So little RE is just 25 millivolts over IC, and as mentioned in the Tektronix concept video that actually talks about transresistance, transistors are imperfect devices. Resistors are imperfect devices. Therefore, we can use imperfect equations.